Terima kasih banyak Pak Surya. I think the introduction is sufficient. Saya bisa bahasa Indonesia, but the presentation will be in English, because I will be able to speak faster when I do it in English. But please feel free, kalau ada pertanyaan nanti, silakan di bahasa Indonesia saja. So the talk is about large-scale, cost-effective mapping and monitoring of peat dome landscapes using LIDAR. And this work I will be presenting, as Pasuria already said, we published recently on mapping approaches using LIDAR, focusing on lowland landscapes, so low-lying areas, including peat dome landscapes. And I did this together with Al Hoyer, who is also in the room, and many other ex-Deltares colleagues. Al Hoyer is still working for Deltares. So these are 3 publications using LIDAR data, which has been published in the last 2 years. And which have been will be presented during this talk, and it focuses on the creation of an elevation model. From that elevation model, creation of a deep peat map, and we have also used the LIDAR data and developed a new and novel method for measuring canal water depths using the LIDAR. All the maps and map products which have been are freely available, and for those of you interested in the maps, they can be downloaded from links which you can find in these papers, and all these papers are open access, so you can find them online and you don't need to have a membership of the publishers. So for those of you who are new to LIDAR, LIDAR stands for light detection and ranging, and it is the most accurate method to derive elevation models, but also canopy height models, for instance. The LIDAR data which we have been using have been acquired on an airplane flying about 850 meters above the surface, and generated between 7 and 10 points per square meter. As you may know, LIDAR is the most accurate method to derive elevation models, but also an expensive method. So that's why we have developed a cost-effective approach by not flying LIDAR full coverage, but flying the LIDAR data in strips, as is illustrated in the top part of this figure. This is, those of you familiar with the area, the Kampar Peninsula, a large peat dome of more than 700,000 hectares. So we have combined the LIDAR strip data and manually delineated contour lines based on the underlying landscape, which we can visualize through other optical remote sensing imagery, and combining the LIDAR strip data and the manual contour lines through interpolation, get a full coverage DTM. So this is the general approach, and I will now go into a little bit more detail, but also considering time constraints, I can't go into too much detail. So we have tested this approach for an area in central Kalimantan, the ex-Mega Rice project area, where in 2011 LIDAR data were acquired full coverage. So we could test the strip method and compare it with a full coverage LIDAR DTM. And then we have applied the strip method for the East Sumatra coastline. And this area has been covered by 30,000 flight kilometers, so it's a lot of data. Most of these LIDAR data have been paid for by HF Pulp and Paper, and part of the data amongst University in England, also the UK Climate Change Unit. So I skipped the whole validation part, which is too much for this presentation now. But what you see here on this map is the resulting elevation model, which covers about 71,000 square kilometers, covering only 20% of this area has been covered by LIDAR data, and the rest through interpretation of the LIDAR data and through manual interpolation. It covers about 80% of the lowland area in Riau, Jambi, and South Sumatra, and it covers 4.5 million hectares of peatland. Well, the accuracy of this DTM ranges between 25 centimeters, which is where we have actual LIDAR data, up till 61 centimeters, and that depends a little bit on the distance from the actual LIDAR strip. Further, what the elevation model shows is that almost 2.6 million hectares of the land is really low, below 2 meters above mean sea level. So large areas will likely to be increasingly flood prone in the future, considering sea level rise and soil subsidence. The elevation model also allows us to identify peat domes. An example of this was shown earlier already, and now here as well on the right side of the Kampar Peninsula. And going into more detail, it also allows us to identify large-scale land subsidence features, as is illustrated here for the Kampar Peninsula, a peat dome which is partly forested and partially a pulp plantation, where you can see where the plantation is drained, you'll see a large drop in surface elevation. Now we are going to the second paper on deep peat mapping. We use an approach where we need an accurate peat surface elevation model, and using peat thickness measurements to determine the position of the peat bottom, so where the peat lies on the mineral subsurface. We are focusing here on peat domes, on coastal peat domes developed some 7,000 years ago, when the end of the Ice Age, sea levels were rising and stabilizing. So the peat bottom is more or less close to mean sea level. We have been testing and validating this approach in two test areas. We have been participating in the Indonesian Peat Prize, and the first area was Bengkalis Island, and the second one was Kuburaya. And we have been collecting peat thickness measurements along transects to determine this peat bottom position. So over here you see the two elevation models. Both elevation models are derived from LIDAR data. And the black dots are the locations of the peat thickness measurements. The black dots where we found peat more than 0.5 meter. And the white dots are areas where we don't find peat at all. We find a very good correlation between peat thickness and surface elevation, with the regressions approaching unity, confirming that the peat bottom is relatively flat and close to sea level, as is also illustrated by these cross sections, where the black line is the peat surface elevation and the brown line is the peat bottom location. So by determining the average peat bottom location, subtracting this from the peat surface elevation, we derived two peat maps for Bengkalis and Kuburaya, as is displayed in these maps. So, because we found these good results, we have validated this for the elevation model for East Sumatra, and we determined the peat bottom position from more than 2,000 measurements, where we have found deep peat, so more than 3 meters in East Sumatra. Over here you find the statistics. The average peat bottom ranges somewhat, and we have applied an average peat bottom position of 61 and subtracted this from the elevation model to derive a deep peat map. We've done some sensitivity analysis. The details you can find in the publication. And in the publication, you will also find our carbon stock estimation using these maps. However, it needs to be considered that part of the peat is below mean sea level, or will be below mean sea level in time. So for carbon stock calculations, it is always good to realize that not all of the peat will be up for oxidation in future, because it will be permanently underwater. What we also found when we superpose the existing forest cover, as published by Margono in 2014, using optical Landsat imagery for the year 2012, we found that the majority of the non-mangrove lowland forests, which is more than 90% of remaining forest in East Sumatra, is actually located on these deep peat domes. So protecting deep peat areas provides an opportunity to not only conserve large amounts of below ground peat carbon, but also the last of the Sumatra lowland forest and associated high above ground carbon stock and unique biodiversity in those forests. This is my near final slides, going into the third paper where we developed a method to derive canal water depths from the same airborne LIDAR data which we have been using to generate the elevation map. And this is the approach. We have an irregular, somewhat irregular peat surface, and we have also laser returns from the LIDAR instrument on water, because there is always some floating debris on that. So by subtracting those two elevation values, we get an instantaneous observation of canal water depth. We have validated this method as well in plantations using field surveys at I think, I forgot the number, but I think we have some 140 up to 200 data points. And also here we find a very good correlation between the field measurements and the observation from LIDAR. And the method here on the map here on the right side shows the differences, where we find that most of the measurements, 86% and 99%, are within 25 and 50 centimeters from the field measurements. We have applied this method on the full coverage LIDAR data set we have for the X-Mega Rise project area in 2011. And zooming in here on block A, we find that most of the canals in these drained peatlands were well below 1.5 meter, often below 2.5 meter, and this was in the dry season. And yeah, with these deep groundwater levels or water tables in canals, is a very high fire risk. So this is my concluding slide. We have been looking at satellite LIDAR data as well, which have been launched by the end of 2018, the ISAT-2 and also the JEDI satellites, which allowed us, this is not full coverage, this is also in strips, so to speak, spaced 3 to 4 kilometers apart. We have been able to generate a global lowland DTM, the very first of its kind, which was found to be extremely accurate. At the moment, the satellites are still acquiring data, but in time, we expect, and actually we are currently working on that, to allow to map the Peat dome. So you will be less reliant on expensive airborne LIDAR data, but you can actually do it freely using the space satellite LIDAR. And in our deep Peat mapping paper, we already had a quick look at a comparison between these satellite LIDAR with the actual airborne LIDAR DTM, which is shown here, which shows a very good comparison. So this provides us with a lot of confidence how good it is. And with this, I would like to conclude the presentation, and I hope there is still enough time for answering your questions. Thank you very much.
Thank you very much, Ronald. We now take some question from the audience. You can also deliver the question via video if you would like to deliver directly, or you can also write in a chat room, dapat menulis di room chat, atau bisa menyampaikan juga langsung. Bapak Ibu.
Silakan.
Bisa bahasa
Indonesia boleh.
Oke, kalau belum ada yang menyampaikan pertanyaan, mungkin saya mulai terlebih dahulu, Pak Ronald. Jadi ada dua jenis LIDAR, airborne dan satellite. Apa kelebihan dan keuntungan masing-masing kedua metode ini, Pak Ronald?
Maaf, maksudnya kelebihan?
So you were discussing airborne LIDAR, and also this one now here, satellite LIDAR. So what is the advantage and disadvantage of if we compare both products?
Well, the airborne LIDAR will be more accurate, but it's also very expensive. So in areas where you don't have access to airborne LIDAR, we also demonstrated in this publication here that with satellite LIDAR we can actually get very high accurate elevation models as well, albeit at the moment still at a relatively coarse resolution. At the moment, this paper was at 5 kilometers. So with I'd say a grid of 5 kilometers, you won't be able to accurately delineate a Peat dome. But as more and more satellite LIDAR data are acquired, you will be able to go to a higher resolution. So for smaller Peat domes, you will have to go to 500 or maybe a kilometer. That's what we are aiming for now. So that will allow at least the contours of the Peat dome to be mapped, especially in areas which are still forested, for instance in Papua. So this will allow at least to get a very first estimate of where the Peat domes are, how big they are. And obviously you would still need to go there to do some measurements and to actually accurately monitor the Peat depth, to map the Peat depth. But the big advantage of this satellite LIDAR is that it's all free. So that's the good thing. And it works also in forested areas, as we have demonstrated as well. Also, this paper is freely available online. And also the map is available.
Okay, Ada pertanyaan di chat room, Pak Ronald. I read it for you from Kerinci. Thanks, Dr. Vernimmen, for the presentation. Do we have any information about peatlands in West Papua and its land use?
Well, there is the government map, of course. Now is the one from PBSDLP, but I don't know how accurate those are. But in West Papua, satellite LIDAR also covers the area, so it should be possible to have a look there to see whether from the satellite LIDAR data peat domes can be identified. And of course, the BBSDLP map could be used to look at what was previously found. Earlier, we did some analysis on the accuracy of this peat map, also the Wetlands International map, which was packaged by Wetlands International, but of course an older version of the BBSDLP map, where we found that the peat extent was pretty accurate, but the depth of the maps were underestimating the peat depth. So in terms of extent, the earlier Wetlands International map and BBSDLP maps are in most areas, not all, pretty accurate. So that will be a very first way to check whether there is peat and how widely it is spread in West Papua. And on land use, yeah, there are many land cover maps available, and I believe land cover maps.
Oke, Pak Ronald, pertanyaan berikutnya ini dari Dr. Bababarus. Anda sudah menghasilkan data DEM di pantai timur Sumatera dan XPLG. Apakah datanya dapat diakses publik?
Ya, semua data yang udah terpublikasi, dan untuk lihat data tersebut bisa lihat di publikasi. Ada linknya.
Okay, good to know. I think Pak Baba is very happy with this information because he's doing study right now in that area.
Okay.
Okay. Sebelum saya melanjutkan satu pertanyaan lagi dari Pak Bismarck. So one important result from this research is that, as you mentioned before, that millions of hectares of land in eastern part of Sumatra below 2 meters above sea level. What is the consequence for the peatland management?
Well, in those very low-lying areas, there is hardly, if any, peat left. So those are already mineral soils or very shallow peat, not even considered peat anymore. So those areas are mostly in South Sumatra, near the coast, and some in Jambi.
This is El Hoyer speaking. If I may say something on the peat management.
Yes, please. Please.
The consequence of we also found that the peat bottom is usually around sea level, right? 0, 60 centimeters, 1 meter, in that range, and sometimes below sea level. And the very low-lying areas in East Sumatra that we see in our DTM, part of those are peat on older maps. So there was peat and now it's gone. So what we see is basically, if you remove the peat, you are left with very low land, which is flood prone. And the consequence, of course, is that if you decide on peatland management, you need to take into account the consequence of draining the peat, having the subsidence, losing the peat in the short term or long term, you can debate how quickly that will happen. It could maybe 10 years, 2,500, maybe more, but it will happen. You will lose that peat because it's just carbon, right? And with sea level rise and the fact that the mineral soil below it is usually clay, which also keeps subsiding a bit, you end up below a high water mark, definitely, already now. And in the future, you're below sea level. So basically, if you decide to drain a peat swamp in the coastal area, in many areas, you decide that in the longer term, you're going to either lose the land or you're going to have polders with dikes and pumps. Those are the two future consequences. Not in 5 years, 10 years, but 25, 50, 100, yes. Yeah, so it's a big consequence, actually.
Thank you, Pak Al, for detailed explanation. So actually, regarding the peatland, it is not only peat fire. So the challenge also the subsidence, which seems not very obvious, but this is progressively going on, and sometimes then the elevation of peatlands also below the sea level. Yeah? I think this also a very, very important challenge to consider.
Yeah, in the future. And sometimes now there are areas in East Sumatra where this is already happening. We know these areas, right? Where it's flooding most of the time. All palm plantations are not very successful or very unsuccessful. We also see it in the ex-mega rise in Block D, which is very low lying in places like Dadahoop, where in some cases there was peat originally, in others there wasn't. But now it's so low that it's very hard to get any production out of them. You know? Yeah.
Okay, thank you very much, Pak Al, for the explanation. Because of our time constraint, I just would like to take one more question from chat room. This is from Pak Bismarck from Kalimantan in the Mega Rice Project area. Yeah, this is for related to the use of LIDAR for water zoning. Ya. Nah, dapatkah Anda memberikan penjelasan bagaimana menggunakan data DEM untuk menetapkan sub KHG? Pak Ronald, Pak Bismarck is asking if we can also use the LIDAR product to map smaller landscape. We call it sub KHG. It is, I think you are also familiar with sub KHG terminology, isn't it?
Ja, sedikit. Tapi, how to say? Well, it's an elevation model, so it depends a little bit on the criteria for how do you define a water zone, and then you can define water zones. It's found it the question a bit difficult to answer here. It's maybe, I don't know, Al, do you have any?
No, as you say, it depends on the definition of the water zones, which is not always entirely clear to us, but we haven't looked at it for some years, I think. So maybe it's changed a bit, but it depends on the definition. It depends on scale, of course. Mm-hmm. If the data that are available are sufficiently detailed to match the requirements for water zoning, you can do it, mm-hmm. I think. And of course, also the water table depth mapping that we've also demonstrated. For areas that are already drained, you can maybe use it to refine the water zoning. So you isolate areas where water tables now are very low, and you say, well, we need extra measures there. But I don't think that's a KHG issue, that's a management issue. Yes, that's all I know what to say to this question. I hope it's helpful.
Okay, thank you very much, Pak Ronald, Pak Al, for very valuable